Hello and welcome to my new course with electrical machines. Now I'm going to do transformers. I'm gonna explain the principle working of transformers. I'm gonna do some examples and in the end I'm going to do some problems, and that's it. Now if you have looked all the literatures for electrical machines, these very popular and very useful books for electrical machines, you know that the first chapter of every for the first chapter, all of those books are magnetic circuits, and I did a course you can find on my YouTube channel, and you can also look at my description a link of the playlist where I did all the examples and all the explanation of magnetic circuits. So if you don't know magnetic circuits, if you don't know that field in electrical engineering, I advise you to first learn that, so that everything else for transformers, AC, DC machines, synchronous machines will be easier to understand for you. Okay, so look at my description if you want to learn magnetic circuits. But if you already know magnetic circuits, what is magnetic flux density, what is magnetic field intensity, what is magnetic flux, what is the exciting current, what are the core losses in those magnetic circuits, then you don't need to watch that. But my advice, if you don't know, watch that. Now I will first do I will going to first explain some theory about the transformers. Then I'm gonna do some examples, and at the end I'm gonna do the problems that I have in my own books, and this is all for college stuff. So if you don't know how a transformer looks, what it looks like, what are the basic principles, my advice for you is to first watch some videos on YouTube, the animated versions of transformers. For example, there is this YouTube channel called Learn Engineering, and they have animated versions of electrical machines. He explains how it works, you can see the mechanical design of the transformer. So you can go to that YouTube channel called Learn Engineering or any other. My focus is on equations, college stuff, learn something, and I am going to explain the mechanical design a little bit, and why do we use this type of transformer, why this, how do we stack them, how do we do the winding, how the electrical energy is distributed through all the country. I'm going to say that, but my advice for you is to look some videos on YouTube, the animated version of the transformers, and also you can type on Google images transformer to see how it looks like. Now, transformers are a static machine. They don't have moving parts, except if you have a huge transformer and you want to cool it down, then people or engineers put some ventilation on those transformers, so that will cool down the transformers. It's a static machine. It doesn't have any moving parts. But we use transformers. They're very widely used in electronic circuits, in power distribution, and that's why transformers are learned in electrical. That's why we learn in electrical machinery transformers. So it's a static machine, and In this video I'm gonna show you some very basic principle of working. So here we have, I draw some stuff on this breadboard. So here is two types of transformers. This is the core type and this is the shell type of a transformer. Now, core type is very rarely used, because I'm gonna say we're gonna get to that. Now, a transformer is used to step up and step down the voltage. It all depends on the purpose of your application. So you can step up and step down the voltage, also step up and step down the current, but usually the main thing is to step up and step down the voltage. Why do we do that? For example, if we couldn't step up and step down the voltage, we couldn't transmit AC energy that long, because when you step up the voltage you step down the current, and there is small heat losses in those transmission lines. So we use to step up and step down the voltage. In my next video I'm going to show you the equations and how do we measure what are the voltages on the how the primary and the secondary. So now here is one type of transformer. It has a magnetic circuit here, and this is called a core type. Here you have the windings, and these windings all share a mutual flux. In practice they don't, but it's neglectable, so we say that these windings share the same magnetic flux. Now, for example, if we have an energy that goes into some winding, we say that that is a primary winding. And if we have a winding where the energy goes if we have a winding which energy goes out, that is a secondary. So energy goes in, that's a primary, and the energy where it goes out, it's called secondary. Transformers don't generate they don't generate electrical energy, they just step up and step down the voltages. So these both windings share the mutual flux, and by Faraday's law, E equals the number of turns times the change in the magnetic flux, then you will have an induced voltage on the secondary, or the secondary winding, where the energy goes out. Okay, now this is a core type, and this is most like a school type of transformer, because you all have flux leakages here and here. So this is shell type. It's we use it more because the windings are on the same magnetic core, and there are smaller flux leakages. And here you have a schematic representation of two winding transformers. So this is the schematic representation of two winding transformers. Now here we have winding on both on the same magnetic core, and here we have a flux produced, and the half of the flux goes in this direction and the other goes in this direction, and there are much smaller flux leakages in the shell type, but they are more expensive to make them. Now, because if you learned magnetic circuits, you know that there are eddy current losses. So how do we reduce eddy current losses? By laminating the magnetic cores. So we have two types of lamination in transformers. This is called the L-shaped lamination, which is used for the core type, and we have the E-shaped lamination, which is used for the shell type transformer. Now, because if we would make a transformer with the magnetic material with only one part, then the eddy current losses would be huge. So that's why we make these tiny, thin laminations, hundreds of them, maybe thousands. It also depends of the design and what are the voltages and currents in those transformers. And that's why we laminate them, so that we will have less eddy current losses in these magnetic circuits. And this is the first layer we put like this, and then we put the second layer on it. And you do that alternatively. We don't use isolation, or insulation, because then we would have an air gap. And if we have an air gap, then we would have a much larger exciting current. And this is used for the E-shaped. As you can see, these are the three magnetic cores, like here, and this is the bottom part. And first layer is going like this, second is going on it, first, second, and we do that alternatively. Now, as you can see here, two windings are on the same magnetic cores, here and here, but in real life we usually put them together, because then there will be one on the other, these windings, because then we have smaller flux leakages in the transformer. And thus lower voltage is usually nearer the core, and the high voltage is on that low voltage winding. Okay, and one more thing, and then I'm gonna do some equations in my next video. This is the distribution, and this is how we transmit electrical energy through some countries. So here we have an AC generator. A generator produces alternating current, alternating voltage, about 30 kilovolts in every power plants. We have AC generator that produces 30 kilovolts. Now, because if the power plants are usually they are very far away from our houses, we need a way to transmit them through the cities, through the industry, and so on. So first, what is it done? What do we have here? Then we transfer this 30 kilovolts into 500 kilovolts. But if we step up the voltage, we lower the current, and that's why we have smaller losses when this is transmitting. That's why Tesla won. This is the basic principle. This is the main reason why Tesla won against Edison in electrical energy distribution. With direct current, you can't make a changing magnetic field, so there is no induced voltage in the secondary. So, if you have a DC generator of 30 kilovolts, that is the you can't step it up and step it down. That you have to transmit 30 kilovolts to household appliances and industry appliances. But with AC, you can step up the voltage and therefore step down the current. And then in the distribution area here, for example, some industries have huge machines, and they need 44 kilovolts of voltage, and so we step down to the 44 kilovolts. Some smaller industry uses 4.6 kilovolts. So we step down the 4.6 kilo to 4.6 kilovolts. And household appliances, in household appliances we use 120 volts. In my country we use 230 volts, but in America, Canada and some other countries they use 120 volts for household appliances. So now this is the how do you say, these are some of the basics, and what I just said, what type of magnetic circuits do we use. If you don't know magnetic circuits, if you didn't conquer that chapter, then all of what I said right now doesn't make sense to you. So you have to learn magnetic circuits. Again, if you didn't learn magnetic circuits, don't watch my next videos. I'm going to do some equations that you are not going to understand because you didn't learn the chapter of magnetic circuits. So, thanks for watching. This was the introduction to transformers, and in my next video I'm going to show you some equations for the ideal transformers. Thank you for watching and see you in my next video.